If you still swipe your card, you're probably handing over data a cloner can copy forever.
Dip the chip instead.
A tiny computer inside mints one unclonable number your cloner can never reuse. Here's the problem the chip was built to kill. The old magnetic stripe stored the exact same data on every single swipe. Copy it once with a hidden skimmer and you could replay it forever. Counterfeit fraud at the register reportedly ran into billions of dollars a year. So in October 2015, US banks shifted the blame to whoever hadn't upgraded to chips. Start with the gold square itself. It looks like a simple metal connector.
It isn't.
Under that plate sits a real microprocessor, a tiny computer with its own processor and its own protected memory. The stripe was dumb storage, like a sticky note anyone could read.
The chip is a locked safe that thinks. Inside, it holds secret keys. Those keys can be used inside the chip to do math, but they can never be read out. They can never be copied to the outside world. That is the whole trick, and it's a physical one. The chip is built to resist tampering. Try to pry the secret out, and the circuitry is designed to wipe or break first. So the terminal in the store, the card reader, even the shop's whole system never sees the key. It only ever sees the answers the chip chooses to give.
Hold that idea, a computer that can prove it knows a secret without ever showing you the secret. But if the store never sees the key, how does the terminal know the card is genuine and not a convincing fake?
Here's the moment it earns its name. You dip the card.
The terminal wakes the chip up with a little power and asks it to prove itself.
It's not asking for a password.
It's setting a fresh math problem the chip can only solve if it truly holds the secret key. So the chip does the math and produces a one-time coded number. In the trade, it's called a cryptogram or a RQC. Think of it as a signature that fits this one purchase and no other.
3 ingredients get stirred into that signature. First, the exact amount of this purchase.
Second, a random number the terminal invents on the spot, different every time, the unpredictable number.
Third, a counter tucked inside the chip that ticks up by 1 on every single dip. The chip blends all 3 with its hidden key. Out comes the coded number. Change any ingredient and the number changes completely. And because the counter climbs with every dip, no 2 dips ever feed the chip the same recipe.
That's why the same card, buying the same coffee tomorrow, still signs a brand new number. But if a thief records that number tonight, why can't they just play it back?
Now watch the replay fail. Say a thief captures tonight's coded number off the wire. Tomorrow they try to reuse it. It breaks instantly for 2 reasons that stack.
First, the counter inside a real card has already ticked forward, so the old number carries a stale count the bank has already seen. Second, the terminal invents a new unpredictable number for this purchase, and the old code was built for last night's random number, not this one.
The recipe no longer matches, so the signature is garbage. Here's the elegant part how the bank checks it. The bank has its own copy of that same secret key, locked in its own secure system.
When your coded number arrives, the bank runs the identical math with the same amount, the same counter, the same random number.
If its result matches the number your chip sent, the card is genuine.
Notice what never happened, the key itself never crossed the wire.
Both sides did the same private math and simply compared answers.
A skimmer sitting on the line sees only finished codes, each one already spent.
It never sees the key that made them, so it can't make the next one.
So what does this actually stop and what slips past it?
It stops the classic clone cold.
A skimmer can copy the chip's readable data all day, but it can't produce tomorrow's valid coded number, because it doesn't hold the key and can't see the future counter or the next random number.
Counterfeiting a chip card at the register basically died. Here's the catch, and it's a big one.
The chip only guards purchases where the card is physically present. Type your card number into a website and no chip is powered, no coded number is ever made.
That door stayed wide open.
So after chips rolled out, thieves didn't quit. They moved online where the old static number still works.
One more thing people get backwards. Tapping to pay is not the weaker option.
A contactless tap runs the exact same chip and the exact same one-time code, just over a short radio link instead of the metal contacts.
Tap is a dip without the friction.
The security lives in the chip's math, not in whether metal touches metal.
So the register got locked. The web stayed open.
Which raises the obvious question, how does the whole system fit together? Now the whole loop clicks.
You dip.
The chip wakes up and mixes this purchase's amount, the terminal's fresh random number, and its own ticking counter with a secret key it will never reveal. Out comes one coded number built for this single moment. The bank, holding its own copy of the key, runs the same math and confirms the answers match. Proof the real card was there, with the key staying locked on both ends the entire time.
That's the core of it.
A stolen recording is worthless, because the very next number depends on a counter that already moved and a random number no thief can guess in advance. Cloning died at the register not because the data got harder to copy. The readable data is still copyable.
It died because the card became a computer that proves who it is without ever showing its secret. 1 unclonable numbers. 0 useful copies. Never twice.
So the habit that matters, dip or tap over swipe whenever the reader lets you. Both power the chip and its one-time number. And since that protection stops at the store's counter, guard your card number online like it's cash, because no chip has your back. Next up, how tokenization hides your real number from websites and mobile wallets entirely.